In this video, we're going to talk about the intersection of a line with a plane, as well as the intersection of two lines. First, the intersection of a line with a plane. There are three cases when we talk about the intersection of a line with a plane. In the first case, the line intersects the plane at exactly one point, and that's illustrated in the first diagram. In the second case, the line doesn't intersect the plane at all, so it's parallel to the plane, and there are no points of intersection, and that's indicated by the second diagram. And finally, in the third diagram, we see that the line actually is part of the plane. It lies on the plane. Every point in the line is also a point in the plane. And there are, in that case, an infinite number of points of intersection. So how do we determine which case we have? Well, we can follow this algorithm here. Set the parametric expressions for x, y, and z from the line into the Cartesian equation of the plane. Then let's assume for this discussion that the parameter we're using is t. We'll solve the equation that we get in part one when we set the parametric expressions of the line into the Cartesian equation of the plane. And when we solve that linear equation, if we get 0t equals non-zero, we'll know that that's impossible because it's impossible for 0 times a real number to equal a non-zero number. That'll mean that there are no solutions, and that would mean that there are no points of intersection, and we likely have, we do have a situation like case 2 on the previous slide where the plane is parallel to the line, or I should say the line is parallel to the plane, but there is no intersection at all. Now, when we, as shown in number 3 on your screen, if we solve that linear equation and we get 0t equals 0, what that means is that there is an infinite number of solutions, and we have a situation like the third diagram on this screen right here, where the line actually is part of the plane. There are an infinite number of solutions to the equation 0t equals 0. And finally, if we get a non-zero quantity times t equaling a real number, then there's one solution to that. And we have a situation like the first diagram on the previous slide, where the line is intersecting the plane at a single point. So suppose we want to determine the points of intersection between the line shown and the plane shown. Well, first thing we do is determine the parametric equations of the line. And we can tell just by looking that the x coordinate on that line is equal to 3 plus s, and the y coordinate is equal to 1 minus 4s, and the z coordinate is equal to 2 minus 8s. We then take those parametric equations shown right here, and we sub them in for x, y, and z in the Cartesian equation of the plane. And when we do that, we get 4x plus 2y minus z minus 8 equaling 0. And we're just going to do some distribution and collecting of like terms and solve our equation. So we distribute in the 4 as well as the 2 as well as the negative 1. And ultimately what we get is that 4s is equal to negative 4. Well, there's obviously one solution to the equation 4s equals negative 4. Specifically, it's where s equals negative 1. So if we go back and actually look at our parametric equations from the previous slide, all we do is we say, well, I'm going to let s equal negative 1, and I'm going to find out what x should equal, what y should equal, and what z should equal, and that's going to give me the coordinates of the one point of intersection. So at s equals 1, we determine that x is 2 and y is 5 and z is 10. And now we've determined that there's one point of intersection, and specifically, it's the point 2, 5, 10. Now, what if we are looking for the points of intersection, if any, between the line shown in parametric equation form and the plane shown in vector equation form? Well, first thing we want to do is recognize that we want that plane to be in Cartesian equation form. So what we're going to do, since these direction vectors are non-collinear, we're going to determine the cross product of those two direction vectors and use that as the normal vector of our plane. we will plug in the 0.31 negative 5 and determine our d value. We'll then have a Cartesian equation of the plane, and into that Cartesian equation, we'll be able to solve these parametric expressions. And then we'll be able to solve for t. So, determining the normal vector of the plane, we simply determine the cross product of 1, 1, 1 and 1, 2, 8. And we see that that cross product is actually equal to 6, negative 7, 1. Well, since the cross product of the two direction vectors of the plane is 6, negative 7, 1, that means the equation of the plane is 6x minus 7y plus z plus d equals 0. Well, we also know one of the but since the direction vector, since the position vector 3, 1, negative 5 is the position vector of this plane, that means the point 3, 1, negative 5 is a point on the plane. We can sub in those values for x, y, and z and solve for d. When we do that, we get d equaling negative 6. So what that tells us is that the equation of the plane in Cartesian equation form is 6x minus 7y plus z minus 6 equals 0. Now, let's take these parametric expressions and plug them in to the Cartesian equation of the plane. And when we do that, we're going to get this equation here. We're going to use a little grade 9 math. We'll be distributing into the bracket and collecting like terms and solving for t. Well, when we do all that work, we end up with the equation 12 plus 6t minus 14t plus 9 plus 8t minus 6 equals 0. When we collect up all our like terms for t, we get 0t. And when we move the constant terms to the other side, we get equal to negative 1. So 0t equals negative 1. Well, we know that that's not possible. You can't multiply a number by 0 and get negative 1. So since we've come up with an impossibility, that means there are no points of intersection between the line and the plane. So L is parallel to, but not on, the plane pi. Now in this third example, we have a line and it's written in vector equation form, so we know that we're going to get the parametric equations. And we have a plane written in Cartesian equation form. We're going to get the parametric expressions for the line and plug those into the Cartesian equation of the plane. So we say that x, which is 3 plus 14s, plus y, which is negative 2 minus 5s, plus 3 times z, which is 1 minus 3s, minus 4 equals 0. Well, we end up, after distributing with this long equation here, when we simplify the left-hand side, we actually get 0s. All the constant terms cancel out, and we get 0s is equal to 0. Well, that's true for all real number values of s. So that means there are an infinite number of solutions. So every point on that line is a point of intersection. Now, what if we're talking about the intersection of two lines? There are 4 cases here. Just like in grade 9, you learn that there are two lines can intersect at a single point if the lines are parallel and there's the lines are not parallel and there's one point of intersection. Okay? Well, the analogy to 3 dimensions is to say the direction vectors are not collinear and there is a point of intersection determined algebraically. Now, it's possible for 2 lines to be coincident, which means identical, if the direction vectors are collinear and we algebraically determine one point of intersection. If there's one point of intersection of 2 parallel lines, then the lines are identical. In other words, what we call coincident. Now, it's possible for 2 lines to be parallel but non-coincident. This would happen if the lines were parallel, or in vector speak, we say the direction vectors are collinear, and there's a point of intersection on one that is not on the other. If you have 2 parallel lines, but there's one point on one of them that's not on the other, the lines are different and distinct. Now, in 3-dimensional space, there's actually a 4th situation, and this is called skew. 2 lines are skew if the direction vectors are not collinear and there are no points of intersection. This is not possible in two-dimensional space, but it is possible in three-dimensional space. So we have the four situations laid out here, and the diagrams for those four are shown. Just like in grade 9 math, you can have two non-parallel lines intersecting at a point. You can also have two coincident lines. You can have two parallel non-coincident lines. And then this fourth situation that only applies in three-dimensional space, not two-dimensional space, is skew lines. So let's see if we can determine the points of intersection, if any, of these two lines shown. Well, right away we see that there is our two direction vectors are not collinear. Those two direction vectors are not scalar multiples of each other. As a result, we know this is not a case of parallel and coincident or parallel and non-coincident. This will either be a case of two non-parallel lines intersecting at one point, or two non-parallel lines not intersecting at all, i.e. skew lines. So that's what's written here. And what we're going to do is determine the parametric expressions for both line 1 and line 2. In line 1, x is 9 plus 4s, y is 1 minus s, and z is negative 2s. And in line 2, x is negative 4 plus 5t, y is negative 1 plus 4t, and z is 10 minus 6t. What we're going to do is set x1 equal to x2 and y1 equal to y2. And what will happen when we do that is we'll get two equations in terms of both s and t. And we'll typically be able to solve for s and t out of those two equations. And then when we do that, we'll be able to check and see if that value of s and that value of t, let our z's be equal. If it does, that means there is a point of intersection. So we set x1 equal to x2 and y1 equal to y2. So 9 plus 4, setting x1 equal to x2 means 9 plus 4s equals negative 4 plus 5t. And doing a little bit of simplifying, we get 4s minus 5t equals negative 13. Setting y1 equal to y2, we get 1 minus s equals negative 1 plus 4t. A little rearranging tells us that s is 2 minus 4t. What we're now going to do is take this second equation, equation 2, and sub that expression into equation 1. So equation 1, instead of 4s minus 5t equals negative 13, equation 1 becomes 4 times 2 minus 4t minus 5t equals negative 13. Ultimately, that means negative 21t equals negative 21, so t is equal to 1. We'll take that t value of negative 1 and sub it into equation 2 and get a value for s. And we see that s is equal to negative 2. So what that means is that when we set the x and y coordinates equal, s is negative 2 and t is 1. That doesn't mean there's a point of intersection yet, though. We still now have to test it on the z coordinates. So using an s value of negative 2, we see that z of the first line would be 4. Using a t value of 1, we see that z in the second line would also be 4. Because these are the same with those determined values for the parameters, that means there's a point of intersection where s is 2 in line 1, or equivalently where t is 1 in line 2. So what we'll do is we'll let s equal negative 2 in line 1, and we'll find out what point we get to. That'll be the point of intersection. So letting s be negative 2, we plug it into the parametric expressions for line 1. And when we do that, we get an x value of 1, a y value of 3, and a z value of 4. So what that means is, and letting t be 1 in line 2 would get us the same point. So what that means is there's one point of intersection of these two lines at 1, 3, 4. So we have two non-parallel lines intersecting at a single point. Now let's try another example. If you're curious, what does it look like when non-parallel lines are skew? It's going to be this question. Right away we see we've got two non-parallel lines because the direction vectors are not scalar multiples of each other, i.e. not collinear. Okay? So since those two direction vectors are not scalar multiples, the lines are not collinear. It means either we have two lines intersecting at a point or two skew lines that don't intersect. So once again, we'll let x1 equal x2 and y1 equal y2, and we'll try to solve for s and for t. Letting x1 equal x2 leads to 3 plus s equals negative 2 plus 8t, ultimately leading to s equaling 8t minus 5. Letting y1 equal y2 means negative 2s is negative 3 plus t. Well, we can take equation 1, this expression for s that we got right here, and we can take that expression and plug it into equation 2 and simplify, and we'll be able to solve for the variable t. When we do that, we end up finding out that negative 7t equals negative 13, so t is 13/17. Okay? Now we take that value of 13/17 and we plug it into the expression we got earlier for s, which is that s is equal to 18 minus 5. When we do that, we get a value for s of 19/17. So we have t equals 13/17 and s equals 19/17. That doesn't mean that there is or that there isn't a point of intersection. We have to now test on the other component, i.e. the z coordinate, and find out. So setting those in as parameter values, we find that if t is equal to 13/17, z2 is negative 8. If s is 19/17, z1 is negative 74 over 17. Those values are not equal. As a result, there is no point of intersection. Since the lines are not parallel, that means we have skew lines. Okay, let's do a question now where we have parallel lines. In this question here, we can tell we have parallel lines because the direction vector of the first line is a scalar multiple of the direction vector of the second line. So that means the lines themselves are parallel. So that means we either have parallel coincident or parallel non-coincident lines. Well, how do we tell? What we're going to do is, so like it says here, since we know the lines are parallel, we'll determine whether they have a point in common. If they do, the lines are parallel and coincident. If they don't, they're parallel non-coincident. So we know the point negative 4, negative 1, negative 6 is on the first line. We know that because the direction vector negative 4, negative 1, negative 6, excuse me, the position vector negative 4, negative 1, negative 6 is a valid position vector for the first line. So if negative 4, negative 1, negative 6, the vector is a valid position vector, then the point negative 4, negative 1, negative 6 is on the first line. Well, let's see if it's also on line 2. So it would, as it says on this slide, be just as effective for us to see if 8, 7, negative 26 is on line 1. So testing whether or not negative 4, negative 1, negative 6 is on line 2, what we do is we say we're going to let 8 minus 6t equal negative 4. And when we do that and solve for t, we see t is 2. Then we're going to let 7 minus 4t equal negative 1, because negative 1 is the y value we're curious about. When we do that, we see t is equal to 2. And then finally, we're going to let this negative 6 here equal negative 26 plus 10t. So if we let negative 26 equal negative, if we let negative 6 be negative 26 plus 10t, t is 2. When we get the same value for the parameter in all three, that means that point is on the curve. So, whoops. Therefore, the point negative 4, negative 1, negative 6 is on line 2. And since the two lines are parallel and they share a point, therefore they are coincident, i.e. identical lines. And every point on either line is a point of intersection between the two lines. For our last example, we're going to determine the point of intersection of these two lines and see if there is such a point of intersection. Well, these numbers are very similar to the last one. And in fact, the only difference is that in this question here, instead of in line 2, the z component of the position vector being negative 26, in this question, the z component of the position vector is negative 16. It seems like my pen's not working at the moment. But just looking at those direction vectors, we see the first direction vector is 3, 2, -5, and the second one's -6, -4, 10. So that means the lines are collinear. And so we either have a case of parallel non-coincident lines that never intersect or parallel coincident lines that intersect at every point. So let's determine whether they have a point in common. Well, just like in the last question, we're going to take the point we know to be on line 1, which is -4, -1, -6, and we're going to see if it's on line 2. Okay? And if it is, the lines are parallel and coincident. And like we said in the last one, it would be just as effective to see if the point 8, 7, -16 is on line 1. Okay, so we're now testing to see if -4, -1, 6 is on line 2. Letting the parametric expression for x2 be -4 leads us to a t-value of 2. Letting the y-coordinate of line 2 be -1, we get a t-value of -2. And finally, letting the z-coordinate of line 2 be -6, we get a t parameter value of 1. Well, as you see at the bottom there, our parameter values are not all the same. When that happens, that means the point -4, -1, -6 is not on line 2. Since the two lines are parallel, but there's a point on one of them which is not on the other, therefore the two lines are parallel and not coincident, and they have no points of intersection between them.